Alright, so hello and welcome. Got another problem to look at today. Let's see, we're going to look at problem number 494, target sum. Let me close these other things here. Yeah, so we didn't need these things. But if you wanted to do that longest subsequences, you can use in n log n time, you can use an interval tree, but I'm not going to show how to do that. But yeah, so target sum. Given an integer array nums, an integer target, you want to build an expression out of nums by adding one of the symbols plus and minus before each integer in nums and concatenate all the integers. Okay, for example, if, okay, this is going to be an interesting question. A lot of people like it. Okay, nums is 2, 1. You can add a plus before 2 and a minus before. This it's probably easy. The ones that are relatively easy, people like. People like to get pat on the back, which I guess is like not the most. I guess it's kind of an obvious thing, but like people like to be, people like getting a pat on the back. I guess people like feeling good. Plus and minus before each integer in nums, and then concatenate all the integers. For example, if nums equals 2, 1, you can add a plus before 2 and a minus before 1. Concatenate them to build the expression plus 2 minus 1. Turn the number of different expressions that you can build, which evaluates the target. Okay, well, ultimately this is like add or subtract the value. Because if it's in the front, it becomes a negative number, right, or a positive number. And then if it's in between, it's so this is effectively adding all the numbers and then deciding what their sign is, which is pretty simple to kind of discern or to figure out. That's actually something I figured out when I was really young. I was like, oh, you can, like, when you mess around with signs of things, like subtracting a number is the same thing as adding a negative number. So anywhere you see a negative number, you could just make it a plus and a minus. So like addition and subtraction are basically the same thing, except it's just when you subtract, you're just adding a negative number. And that's kind of, this is like a question where that kind of idea really comes to the fore. It's only 20 numbers to work with. They're relatively small. Yeah, so I mean, this kind of looks like a backtracking question, like a DFS. I think we've done this before. 2 raised to the 20th is only 1,000,000. So there's really, so they want all of them, right? The number of different expressions that you can build. Yeah, I mean, okay, we'll just do DFS. I don't know. There's maybe a better way to do this, but I don't know. I don't know what it might be. So, oh, you know what? This might actually have a dynamic programming solution, like quadratic, similar to what we did before, quadratic time dynamic programming solution. Let's do the DFS first and just see if we can get it right. See how long it'll take us. We're 3 minutes in? Okay, so let's see. Let's do DFS. And we're going to have an integer, and we're going to say we have a state, which we're going to just say is so how are we going to run this DFS? Well, we'll have an int, I think. And well, I think it's just that simple. So for int I equals current plus 1, or just current, I is less than nums dot size plus I, val equals nums I. We have f of, so we have int lesser, int greater, and current plus I, And so this lesser is going to be a negative val or a positive val. And that's current plus I, it's current, or it's I plus 1 rather. And F, and then that's it actually. That's pretty much it. Whoops. Not it, but like pretty close to it. I think this is all we gotta do. I don't know, maybe I'm missing something. What does this do? I don't know. I don't know. Does this even compile? Let's start with that. Wait, what? Oh, oh. Oh, that's my mistake. I didn't really think about that. No, I'm doing this wrong. I need to modify the state. I need to actually have a state that's being changed. Yeah. That's my mistake. Yeah, I don't know. I'm doing this incorrectly. Current total minus equals val f of I plus 1 current total and then f. Yeah, I mean, huh. Sure. I think it's, am I crazy? Like it's yeah, it's like super simple. It's super easy. Like I don't know. Am I just nuts? Is this that easy? I don't know. My brain is, sometimes it's like it's so easy that you just can't think straight. Or it doesn't make sense. It's so easy that it doesn't make sense. Is that, or maybe not. Or maybe not. Expected 5, 3. Okay, you could do 1, 2, 3 different ways. But there's also 1, 2, 3. Also 1, 2, 3. Oh. No. What? Wait, what? How did we get 15? And how is that wrong? Wait a second. What? thought this was simple and correct. 10 minutes, okay. If the, oh, because, oh, I see. I see, okay. It's gotta be, this has gotta be out, oh, I see the problem, yeah. 1, 2, you have to use all the letters, so 1, 2, 3, 4, 5. And current is, okay, I get it. So current's gotta be equal to, notice that size. I think that's the issue. Oh, still wrong. What? No. Yes. 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 But why is it still wrong? What? It's really the other way around, right? I mean, it shouldn't matter. If this is larger, then this doesn't do anything, right? So this should be fine. Now, why not though? Okay. We can have a sequence, I guess. Yeah, we could do it that way. Sure. It's part of the state. I don't, I don't know, I'm really confused. Excuse me. Should be negative value. What I'm confused about is what did I do wrong here? I did something wrong here. I don't know. I don't know what I did though. I think you don't use a for loop here. I think that's the issue. I actually think that's the problem. I think it's actually that easy that I'm tripping myself up. Which is maybe a little bit confusing. I think that's the problem. Yeah, it's actually that simple that I'm just not doing it right. Don't think we actually need the sequence. Yeah, I think that's what I did wrong. Maybe I'm crazy here. This definitely can be, you can use that. I think you could definitely use dynamic programming for this. I'm sorry, what's going on? Oh. Oh, okay, okay, yeah. Right. Good thing we practice. It's a good thing we practice. Oh boy. Okay. Okie doke. Let's go to 20, right? We'll go to a whole bunch of numbers. Let's do one number. Let's try a bunch of different numbers. It's negative oh no, the numbers are all positive. Oh no, yeah, numbers are all positive. I think between 1 and 1,000 as well. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right. Yeah, I think this question is so easy that it was hard. Something like that. Oh, we need, I don't know, 500. 100, negative 500. So the nums are between 0 and 1,000, okay. One of these over 1,000? Oh, can't be 0. Okay. And okay, let's see. No. Oh no. I'm sorry. No, it could be 0. What is the test case that's failing? Oh, this negative number, it can't, none of these numbers can be, okay, I think I get it. None of the numbers can be negative. The target can be negative, but the values themselves can't be negative. Okay, oh, and the sum is less than 1,000 as well. Why is that? I think that's what this is failing on. We could just decrement these, I guess. 300, 235. Let's not have 300. Try to get these test cases to work properly here. Okay. All right, I'm going to save these test cases because I lost my test cases before. Is this correct? I don't know. Let's see. Maybe, hopefully. Is there a test case I missed? No! Wait, what? Wait, what? Only 20 numbers. How? What? What? Excuse me? Oh. Huh? I mean, interesting. Did I only go to 15 and not go to 20? And that was fine on this. This isn't TLE. What? Excuse me? What do you mean TLE? What? There's a TLE here. Huh? What? What? Did it just bug? What is going on? Excuse me? Does it not give you all of the details? Took too long? I don't, okay. Alright, whatever. Fine. How is it even possible? What do you mean it took too long? What? It's only 1,000, it's only 1,000,000 things. Okay, fine. I mean, I think that this has an optimization or two, one or two optimizations that you can make. But it's definitely interesting this times out. Okay, sure, I guess. Excuse me. Okay, so can I optimize this actually? Is that even possible? Huh. I don't know if I can, man. I don't actually know. It's interesting that this TLE's though. I wasn't expecting that. Huh. Huh. Hmm. Hmm. How did I miss that? Oh, well, it's fine. It just doesn't, for some reason, doesn't work. I don't know. I don't know. How does that happen? I don't know. That's really strange. Okay. 22 minutes in. All right. Uh, excuse me. Excuse me. I mean, I don't know, man. Is this faster somehow? Is this better? I mean, it doesn't take that much time. I don't know. 139. Maybe that's why, because 139 test cases. Do 139 times 80 milliseconds each. It's too long, right? That's 11 seconds. It's too slow. So, well, okay, we can definitely optimize the depth first search, the backtracking by removing, doing some branch pruning, right? Like that we can do with certainty. We can prune some of the branches. Basically, if adding all the numbers or subtracting all the numbers that are left would give you something that's doesn't get close, doesn't is gets yeah we can't get close enough. Basically, if adding everything or subtracting everything doesn't bring us close enough to the, well, okay, we put it this way: if we added everything and we're still larger, excuse me, still smaller than the target, or if we subtracted everything and we're still larger than the target, then we've gone too far. We could prune those branches. That might optimize this slightly, and then we can submit it and be happy. Not TLE. Could try that. Really surprised at what we're looking at here, but okay, we can try that. Let's do that first. Let's do that first. So we can do what do they call that? Pre-computation. Optimize sum, range sums. Yeah, we'll just say consecutive subsequence sums. So we're going to say standard vector of ints, we're going to say sums, and we're going to say for const auto x and nums, sums dot pushback back plus x. Oh, it's a baby. Surprise baby. And then we're going to say nums dot push back nums of 0. I think we have to have at least one number, right? Yeah, so there's at least one number. Not nums, but sums. Sums and nums here. And then we want to say auto summation is going to be like the following. IN, or IJ rather. So this is inclusive. I'm going to say sums of J minus sums of I. We're not going to do any balance checking plus nums of I. Yeah, we're not going to bother with balance checking. So backtracking. Find all possible combinations. Lead desired target. And now we say if current total plus summation of current plus 1 to the end, which is nums of size minus 1. If that's still less than the target, or current total minus summation remaining sum. We could just slightly optimize this. I think the compiler would optimize this anyway, but or yeah. So if you add everything left and you still won't be able to make the target, or if you subtract everything left, you still won't be able to make the target, then you just cut it off right there. You just go ahead and say forget it. Prune branches that certainly will not make it. Not make it. Yeah. Nice. Runtime error. Sweet. We have to say, yeah. Current is less than nums dot size. That's 1. That's why we got a runtime error. It's because we did not do that properly. Yeah. Hopefully this makes sense. Hopefully this makes sense. That's not where we got the runtime error. Nice. Why did we get the runtime error? Oh, because yeah, actually we should put this below then. Because we're already doing the check here. If it's equal to the size, it actually needs to be, no, wait, no, never mind. That's kind of annoying. It's gonna make things a lot slower. Yeah. Okay. All right, never mind. We're We're gonna go ahead and do it this way. Exactly what I was suggesting before. I don't know, maybe there's a way to slightly optimize this, but we're gonna go ahead and do it this way. Sure. What? Oh, I see. We don't actually need this. Sorry, I'm kind of working through these different combinations of things. Oh, still wrong. Okay. What? What do you mean it's faster, but it's wrong? Of course it is. Why would this be wrong? Why would that happen? I think the last sum. Okay. Nice. No. Okay. So if you have one less thing, if you add and you're less than the target, or you subtract and you're greater than the target, then return. Yeah, I mean that's dead branch there. What are the one things we're missing though? We're way off, huh? 5 and 2. Okay, so I got 2 for the top one for just ones. Why though? Why? Excuse me. So if we don't prune at all, it should still be correct. Let's just make sure that we're at least there, right? Before we really lose our minds. Okay, so yeah, so we're pruning too much somehow, but that's not true, right? Because oh, I think I'm wrong about this prune. If you added everything and added it to the total, and you're still less than the target, yeah, you should stop there because you can't. Nothing after that point will work, right? If you add or subtract after that, it won't matter. If you're greater than the target, well, yeah, well, right. No, I think, or if is it? Am I crazy? Am I crazy here? Something's not right. Oh, because when we add current, oh, that's why. Okay, understood. Never mind. Never mind. I was wondering. In that case, we can actually do the thing we did before where, got it. Okay. We kind of slightly changed the code where we add the value here instead of before we were like, yeah, okay, never mind. All right, let's see how we do. That's my mistake. Does it work? I don't know, maybe, possibly. Seems a little bit faster. No, still TLEs. Nope. Still too slow. Still too slow, bud. Still too slow. We don't need this anymore. Oh, oh boy. Does it work? Does it work? Yeah, okay. Let's see. I think we're still too slow. Oh, okay. There we go. We got it. All right, dude. That was whew, whew. Wow. All right. So we're at almost 37 minutes, and we high rolled or we low rolled, high rolled, we high rolled the successful. Oh, we just made it. Wow. Okay, that's pretty funny. I don't know, man. I mean, having 140 test cases does make it kind of challenging, and it's supposed to be under like a few seconds. So, but I think there's a way to do this. I could be wrong, where you can optimize, use some dynamic programming. So let's memoize this. Let's start with that. So we're gonna say, yeah, let's try memoizing, see how that goes. Yeah, let's give it a shot. So if we memoize this, let's use a map. Let's try that. Start with that. We're gonna have two integers, current and current total. Actually, I don't know, man. I don't know how to. I actually don't know what to do here. Excuse me, because this is not. No, I don't know. I don't know. I actually don't know how to solve this, or at least how to make. Yeah, there's like a. So, okay. So memoization does what? I don't think it does anything for us really, because we only have a solution when current is at a certain point, and when the total, like all of our solutions are when these are equal, right? So like there aren't any. Do we save? Are we true or false maybe? Return true, return false. And we terminate early if we get to a point with a certain amount and we know that there's no solution, or we know that there is a solution, or how many solutions there are. You can maybe do it that way. You can accumulate the solutions. It might work. So can we do it that way? So we have, yeah, maybe that. I think that's what we want. And then we can memoize that, maybe. Something like that. I don't know. Okay. Now we'll return 1. If that's true, then we return 1. Otherwise, return 0, right? And here we return 0 if it's not possible. Excuse me, still prune. And here we're going to return both of these possibilities. So we say int sort of left and int right. Call it left and right. Something like that. Or greater or smaller, whatever you want to call it. I don't know. Okay, it's still right. Yeah. So now we can memorize this, I think. Now let's try map. Now, what's interesting about this question is that I think using the map is going to add so much extra overhead for each case that this isn't going to work because it's kind of expensive to do it this way. So I think it's not going to work here. Try using memoization. I want to say dynamic programming is ultimately what we're going to use to make this a lot faster. Okay. Okay. What does this do? Does this still work? And is it too slow? No, it's not correct. Nice. Really? So you can't memorize this. Are you serious? That's not true. What? 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 Oh, that's probably has something to do with it. That could be it, actually. Pruning. It shouldn't matter though. So we just ignore the memoization, what happens? Still wrong. I don't know how that happened. I don't know how that happened. What? I'm so confused now. What? We didn't. It was working just a moment ago. What? What? How is this working just a moment ago and suddenly it doesn't work anymore now? What is going on? What? Hold on, what? Before we added the memoization, this was working. Am I crazy? Am I losing my marbles here? Huh? What? Oh, I think I know what happened. I know we did wrong. I got it. I know what happened. That's so confusing. But I know what we did wrong. I'm sorry. That's my mistake. I'm dumb. I'm dumb. I actually do know what's wrong here. This is no longer a that's no longer a single block. That's, I don't know if that's a bad habit. Like, I kind of don't like writing if statements that don't have these braces, because you could do stuff like that where the fall through you forget about, and then your program doesn't work properly because you added memoization, for instance. That's like such a subtle thing. But okay, let's see. Are we faster or slower after this? Better or worse? Hey, oh, we're a lot faster. Whoa. Hey, there you go. Okay. All right. So definitely memoization can be done. That makes this algorithm quadratic in time. And you actually don't need this value. Well, do you? Yeah, I guess you kind of do. Yeah. Okay. You can do a vector of hash maps, by the way, instead of this map here. So yeah, you can definitely do quadratic time. It's actually not quadratic. It's this times this, which they kept this kind of small. I think they kept these the same size, but it's an interesting question. A little bit more challenging than I thought it was going to be, by the way. I thought this was going to be easier. So you could do a dynamic programming solution that gives you quadratic time. We can do, you can allocate the memory directly as well if you wanted to, which is a little bit better. You can do a vector of vectors. And since we know everything's gonna, be positive, then we can use any negative value as a sentinel value. I don't want to look at the discussion here. How long did this take? We kind of got nailed in this question. Pruning with memoization. We can also do. Could probably remove the pruning too if we wanted to. How do we optimize this further? Can we do better than quadratic time? I think we can. We can also kind of do this problem in any order that we want. So yeah, I mean, you can actually do things the other way around, where you start from the sum and then you select values to subtract, and you only subtract values. So if you go below the target, or you do the other way around, you could, well, yeah, actually it's probably easier. You can do, yeah, you only subtract, so then you can go below the target. And if you do go below the target, then you can stop there, terminate early that way too. And I guess you can say, okay, all of the sequences that contain one or don't contain one. That's kind of what we're doing. right? Either you contain this value, or you don't, or you subtract this value, or you don't subtract this value. Can we do it in linear time though? I don't think we can do it in linear time. I don't think so. Maybe. Feels like you can. Seems like you can. Do you want to start from the target and go down, or start from a negative value and go to 0? Not from the target, but from the sum to the target. Excuse me. With the summation to the target. If we go negative values to the target, I think it's better to go with the total sum down to the target, given the constraints. From below up to the target, yeah, I think it's actually, because then that's actually more space to cover, I guess. So I'm thinking if we're going to use a two-dimensional array to store these values, how we're going to do it. Only working with 20 numbers, right? Yeah. And the sum is 1,000. I want to go to bed. Just thinking about this here. Calculate the sum, we can allocate space, we can say, we can use dynamic programming. Two-dimensional array. I don't know if we could do better than quadratic time on this. Could definitely get much faster runtime if we use dynamic programming, which I'm going to look to do that right now. But first off, how could I have figured that out immediately instead of going through all of this stuff in between? That's one question. The second thing is, excuse me. This is an interesting question. This is, by the way, related to how many ways can you, this is related to how many subsequences add up to a value, to a specific value. Very similar. Actually, I think it's the same question, just phrased in a different way. Yeah, it's basically the same question. As I said, I don't think you can do better than quadratic time. I think that's the best you can do. Let's try to get that. Let's try to do that. I am not going to bother with the excuse me. Actually, no, we can still do that. We can still prune. All right, let's prune. Let's also not backtrack. Let's use DP instead. I'll show you what that looks like, or take a look at myself what that might look like. All right, so DP solution. Not really sure how to express it. and we're going to say it's going to be result or memo, so just dp, and we're going to say nums.size, right? And then we're going to have each of these vectors of ints are going to be of size total. It's going to be summation of 0 to nums.size, or really it's just sums.back. Yeah, we'll just put right in there. And they're going to be initially at -1. And we're going to say double for loop. Actually, I don't know if we can do pruning the same way that we might do it using backtracking, but we can do what was I going to do here? Yeah, so we start with the total. Excuse me, which I think we should have here. And then we actually subtract twice from the total. Subtract twice the amount. From the total, we subtract twice. A particular number. Okay, so we'll do start with I equals 0, I is less than nums.size plus I. And we're going to say int val equals nums of I. Now we're going to say, so for each entry, we're going to subtract that entry by twice val. Is that the way we want to do it? I don't know if we need to do it this way. I don't actually know. Each entry, we're going to subtract this value or not. And the next spot, I'm actually really, I got lost. I'm confused now. How does this translate? Well, what we want to say is, oh man. Oh boy. Sorry. I don't know, man. Excuse me. I'm tired. I need sleep. I know there's some way of doing this, but it evades me at the moment. What is in our array initially? What does our array represent? Our two-dimensional array. What is it supposed to be? Well, it's really a vector in an unordered map. It's actually just a memoization of what we were just looking at. Calling f though, basically we would say. So I think these all should be 0 initially, these values, right? And the DP part, actually this should DP backwards kind of a thing. This should be, you basically just replace f with the DP. So we're not returning 0, 1 anymore. We're returning the total. Yeah. Okay. So for a given amount and an index, there's a certain number of iterations from there that we can get. So excuse me, but we need so actually we're kind of reversing things, but we would say I minus 1, I guess, and this current total minus, we add these two things together, and that's what our dp of I is going to be equal to something like this: dp of I of some current total, something or other. So I guess you do it that way. You say for int x equals 0, x is less than I think that's kind of a challenging thing though, because that doesn't seem to make a lot of sense. dp of I dot size, I don't know. I don't know about this one. I don't even know if a straight translation really makes sense here. Yeah, there's dp of current total x, we'll say that's going to be equal to this sum of these other two, I plus 1 x minus this value plus dp of I plus 1 x plus this value, something funky like this. I don't know. This doesn't make any sense, but my trying to wrap my brain around this. Hi William, how you doing? Hello, Malik Ben Marah. Let All is well. How are you? Welcome. Hello, hello. I'm just struggling my way through some coding questions here, some interview questions. Struggling my way through it. I don't know, man. It's something that I tend to struggle with, is like converting something that's like a recursive, memoized solution to a dynamic programming solution. The same solution is typically not too hard, but when you try to change the solution slightly, that's when I can't trace the two of them. Because what this really should be is like literally the same code, but a vector of a hash set, and yeah, a vector of hash maps, actually, vector of hash maps. And the hash maps should be where you set these values, and the vector part would just be indexed by this current here. And you would memoize that way. Really, that's what this would be. This would be a memoization. Instead of a map, you do a vector of hash maps, and then memoize that way. And then to convert this to a dynamic programming solution, you would... Now the thing is, I think... The thing that makes it really challenging to convert this to a dynamic programming solution, instead of just like memoization that's not using a map, makes this particularly challenging is the set of possible values at the end. Some of them are target and some of them are not. And you don't know that ahead of time. So actually going backwards to try to memoize from those values is sort of logically inconsistent, right? Because you wouldn't need to solve the algorithm if you knew what possible values would have, what target values you could have already, I guess, if that makes sense. What sums you could have. Yeah. A little bit confusing. I realize, a little confusing. So this doesn't make sense. Let me just comment this out because this doesn't make sense either. Yeah. Okay. I also want to go to sleep. I also want to go to sleep. It's pretty advanced. Yeah. I guess. I don't know. Maybe. There's also a thing that can be done where instead of using an unordered hash map here, you can use another vector, because you can say instead of adding and subtracting values to get to a total, you could either subtract twice. You could start the starting point, instead of starting at 0 and adding and subtracting things, you can start from a sum of everything, and then what you're going to do is either subtract twice a particular value or not, right? So subtracting it twice means you flip the sign from a positive to a negative. So now instead of adding, you're subtracting it, so you actually subtract twice, because you're starting with the sum of everything, so everything added together. If you do that, then your hash map actually doesn't need to be a hash map anymore. It can be a little bit more efficient, but that's just like a slight optimization on the original solution here that we had. And what would happen is you would do current title minus twice the value, and then current total just wouldn't change here. And then your current total, your starting point would be a total sum. But that doesn't really matter either. it kind of doesn't matter either, because it kind of goes back to what we were saying before about like we don't know. I don't actually know how to convert this to just a straightforward dynamic programming solution. Because you kind of gotta go backwards, I guess. Hmm. There's a if I could use dynamic programming here, I actually might be able to also get a memory optimization here too, where you don't have to use as much memory. Like right now, I'm using this memoized function. I guess this memoization basically is storing technically a quadratic amount of space, I think. Which you don't necessarily need all that memory. You don't necessarily need to, like, if you can get a dynamic programming solution that has sort of like a level order traversal through the tree, so to speak, then you only need to keep part of the tree each time. Which I think this does have that property to it, because you only need to really keep track of all of the values of the intermediate steps, I guess. I don't know. The problem with it, though, is that if you could know what the values are at the bottom of the tree, because this is kind of like a tree, I guess. You can think of it like a tree where each node has like an amount, and then left side, right side would be left side is subtract a certain amount, right side is add a certain amount. It's a challenging question. Just came here from your Node.js runtime video. Oh, you did? Oh, yeah. Hey. Welcome. Yeah, my Node.js video is way more like, what do you call that? Meant for like an audience. The things I'm doing now, I literally just like turn on the stream and just kind of like try to study a question or work on a problem, and it's way less like, I guess, yeah, audience friendly, because I'm just kind of like lost in my own thoughts. I made that video I think 2 years ago. I've thought about making a lot of other videos that are like that, where I'm just kind of describing stuff in a few minutes. I feel like people would appreciate that on the internet. I feel like the video, I sense. Some people think like I feel and I think are like, it's important to make the distinction because feelings are not necessarily logical, but actually sensing something is kind of a logical thing, because it's like you get a sense for something, and it is like you perceive something. It's not necessarily a sensing, feeling, and perceiving things are not necessarily illogical, right? If you feel a certain way, or you feel that something might be a certain way, you could be incorrectly. Like, in other words, if you put your hands on a table and you say this feels like a table, or you put your hands on an animal and you say this feels like a certain kind of animal, or it feels a certain way, like that's not quite the same as like I feel about something. It's like, I don't know. It's kind of a semantic thing, but a while back somebody was saying like, you don't feel about it, you think about it. I was like, no, that's not really true. It's a mixture of thinking and feeling, right? It's like perceiving things and get a certain amount of guessing too. There's a whole mix of things in there. I think it's fine to say I feel a certain way. Anyway, sorry, rambling on now. But yeah, yeah, the video, the live streams that I do are definitely way less like accessible. Maybe that's the right word. Like way less entertaining, way less like understandable. Excuse me. Yeah, I mean, I thought about making other videos too. Like, there's just like a million things when you're dealing with computer science and programming, like things that happen during employment, things that are like just really like you just have these questions. Here's a question that, like I could make a video on. Like, what is blocking? Like when people talk about blocking. Oops, hold on. And you'll see it all over the place, like non-blocking I/O and blocking this and non-blocking that, and you're like, what does it mean to be blocking? Like, why does everyone think I just know what that means to block? Condition variable class synchronization primitive that can be used to block a thread or multiple threads at the same time. So another thread both modifies the shared variable condition and notifies the condition variable. I think it means to stop a thread while you're yeah, I think it means actually stop a thread. But like, I still don't fully know what it means to block or non-block, because you just see it all over the place and you're like, I don't know. It just means to wait. It just means your thread is waiting. But then you have like blocking for signals or something, and it's like, what it just means it's waiting for a signal. So blocking just means waiting. But like, that's another example of something that like I could very easily make like a 5 to 10 minute video of just like, here are all these places on the internet where they just assume you know what blocking means, and then he's like, here's the spot where you finally understand. Like, it just means wait. It's not, it's all kinds of jargon and stuff. It's just, anyway. So condition variable. What is this? This is the thread support library. Yeah. I don't know. I mean, maybe I don't know. That's the thing. It's like there are all these questions that I end up coming across when writing code and programming and learning about stuff. It's just like, wouldn't it be nice if someone just explained just this one little piece of information? Yeah. So anyway, that's blocking. In case you wanted to know what that was. Yeah, I gotta dig into this thread library too. This is definitely pretty complicated and has a lot going on. And I guess it's not that complicated, but it's something I should look into. So I just know it pretty well. JThread, what's a JThread? Excuse me. Since C++20. Same behavior as a standard thread. JThread automatically rejoins on destruction. Can be cancel stop in certain situations. So one of the things that is really useful about what's going to call like RS or scope-based resource management is that when exceptions are called, the resource is still released. Whereas if you try to manually handle your resources, if you don't carefully handle exceptions and things, then your object won't be released. You have a memory leak, a small memory leak, potentially a large memory leak too. Excuse me. Yeah, and so you have threads that are, I guess, that haven't rejoined when they're destroyed, which is a little bit odd. Would not have expected that, but yeah, join thread, I guess, is what the J stands for. Interesting. Anyway, okay, let me get back to what we're doing here. I don't know how to solve this. I don't know. I'm like kind of at a loss. Like I said, I have an idea to memorize this a little bit better, but then I don't know. I don't actually know how to. there's like a tree structure. Let me just see, what does this algorithm look like if we kind of like visualize it. Have a node at the top. It says go left, go right, so it's plus val, minus val. This is for I is 0, 1, 2, dot, 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 all the way to n. And v of I basically is what we're adding and subtracting. And initially we start off at 0. And so we plus v1 or v0 minus v0, and then this is plus minus plus minus. You know, plus v1 minus v1, same thing, plus v1 minus v1, and then it keeps going. And there's some pruning that we can do where we know that if we add everything left or subtract everything left, we won't get to our target. And then we also have some memoization where we say, okay, you know, some of this stuff overlaps, some of these values. And that's kind of where we're at, and it's efficient enough, but it's not the best. And I want to say something like you could have like probably just two arrays really, where you have like all these numbers, right, in one array, and then you say, okay, we're going to either add v 0 or not, or actually in this case we're going to subtract 2 v 0 or not. And then now we have all these other numbers now. We've just doubled the array, I guess. Some of these are unique, but some of them are not. And all these numbers, they go, well, that's not really, I mean, I don't know. I don't know what I'm thinking here. I don't know. For some reason, it feels like it seems like there's something here. Encourage you to do other videos like it. Yeah? Thank you. Appreciate that. I'll think about it. Thanks. I don't know. You know what the problem is? I feel like I don't have a lot of time. That's the issue. And it's ironic that I say that, or ironic that I express that this way, because I spend all my time trying to get better at programming, and that's why I don't have time. Sort of. You work on projects through React and Node? Not right now, no. Well, kind of. So at my employment, there's a project that I work on that's React and Node. I'm probably going to be looking into at some point. Oh, I don't know when, but actually, right now I'm working on. I'm like, I haven't even started it. Okay, so there's an upgrade or an update to the software system at my job, the company that I work for, that it would help them a lot, or it would help make one of the systems become a lot more user friendly and a lot more useful too. And I want to actually write that in C++. It's has a lot to do with like parsing different configuration files, and it does a lot of like, it's almost like if you could imagine a whole bunch of different machines that have different configuration files, and they all connect to each other in certain ways, and you basically want to have like a like parse all these configuration files and basically create like a map, like a graph, and then process queries on that graph. Right? That's kind of what the program would do. And I'm looking to write that in C++, and I've been kind of putting it off for a long time because I'm busy at my job. That's like something I'm doing in addition to the other things. However, what's interesting is that the output for that program is going to be processed by a web server, I guess. Yeah, I guess web server. That's something that's connected to has a front end UI, which is built in React. And the back end is actually kind of a mixture of like Node and Python, because Python does some things sort of on another, I guess, like through another sort of another process entirely, and then it sort of interfaces with the web server, I guess. But we don't really have like a proper backend, which is weird also because the Python portion was kind of acting as the backend in some sense. So it's sort of a very minimal sort of node backend. So what I want to do is learn about. I think I was gonna go with Express and learn about some like a proper node backend, and build that out. So I would have these two pieces that I'm working on. So one part is the node backend that I want to implement and add, and then I want to also write the C++ small C++ project, and also sort of connect these two things to each other so they can interface, and then that would improve that website a lot. It's like a web page. It sort of gives you like it's an interesting tool. I'll just say that it's an interesting tool that we have, and I mean I don't know, like I haven't had the time at work to, because I'm the job that I have is like it's sort of like a constant stream of stuff that comes up sort of randomly, and I also get kind of exhausted too at my job. Like I just get so frustrated sometimes that I'm like I don't want to work on anything extra right now. Like I just want to breathe, just relax. Let the day go by. After work, I'll I don't know, do something, whatever, think about things. Yeah, sorry, I'm rambling on now. But basically, I have a small project at my job that's React and Node, but I'm like pretty far behind on actually like making progress on it, or I'm pretty far from making serious progress. As far as like in my day-to-day outside of work, I don't know. I kind of like the project I'm working on right now. Obviously, is the one that you're watching, which is I'm trying to solve all of the problems on LeetCode, which I think I could do that relatively quickly. But I don't know. I'm like kind of struggling recently, where I'm like, these questions are just something about it. It's like it's hard for me to quickly solve them. For some reason, like I'm just struggling. But I think I just keep going. After a while, I'll start to see the patterns and start to kind of figure out what it is that's slowing me down. But it's like the dynamic programming questions. There's like a ton of them. I mean that's fine. This is what it is. But like those are always really challenging to like do optimally and do them quickly. Yeah. So I'm working on that. But once I get through solving all these problems, then there are some projects that I do want to work on that I would like kind of share with the world. I guess live stream type things. Like there's a few different things I think would be really really interesting. But like I said, I've learned a lot about like web development. I guess sort of over the years, and I've just learned a ton of stuff, and I kind of just want to like put some of those things together and make something kind of fun, something interesting. I don't want to talk about too much, but it's also kind of sad because there's like so many projects over the years that I would have liked to work on, but like I just never did them. And I was always like, oh yeah, I'm not going to share this idea with the world because I might want to do it at some point. It's like you're never going to do it if you're just constantly distracted with other things. Like it's not. I don't know. But yeah, I've been extremely distracted as of late, just with my life. It's just like there's just so many things to think about and ponder and work on and all that. But anyway, let me speaking of being distracted, let me come back to this question. I'm just flat out nothing. I got nothing. I don't know. What to do regarding this question. How to use dynamic programming here. So if let's say we say we can rewrite this to be let's do 200. Could at least rewrite this and say we start at a total, which is not 0, but it's just the total sum. Call it t, and then we either have don't add 0 or v0, or don't do anything with v0, or subtract v0. And this is I is 0, 1, 2, ... right? And then again, this goes back to t, or we subtract v of 1. And here we don't subtract anything. We just have, you know, negative 2v is 0, or we have negative 2v0 and negative 2v1, right? And then it keeps going. And this is basically the same algorithm that we just had. But why is this significant? Why would we want to do that? Well, it doesn't really simplify the problem that much. And also this is, once we get to there's some target t, we'll call it, I don't know, x. Like when they're equal to x, then, and it has to actually be at the bottom when it's equal to x, then it's a contributing leaf. When these leaves that are the different possibilities, when they're equal to x, then we return a 1 for those values and return a 0 otherwise. And basically these leaves are just sums, or these different values are going to be the what do you call it, these different values are going to be the sum of the subtree, basically, once it's evaluated at the bottom. But the thing is, like, if you could just get straight to the bottom and then take the summation, like that's all you need, right? It's just zeros and ones, you're adding all that together. The problem is that you kind of need these in-between nodes in order to get to the leaf nodes. That's kind of the issue. And obviously we could do pruning, that's what we were doing before. We know that given the sum is bounded, we know that some of these values are going to overlap, so the dynamic programming speeds things up a bit, because some of these nodes are going to be the same node, I guess. Different sums are going to kind of collide, I guess, or something like that. Which means this is going to be big O of n times, I guess ultimately it's going to be times this value, this sum. So O of 20 times 100,000, just 20,000, just not particularly expensive. Yeah. Is there a way to do this better? I don't know. I'm tempted to. I actually don't see a way to do this using dynamic programming that's different from like searching the whole tree. That's kind of what I'm struggling with here, is like how could we search this tree more efficiently aside from pruning it and using some dynamic programming? I don't think you can, realistically. The more I think about this, I don't think you can. I think you're kind of stuck with this. It's not actually quadratic time, by the way. It seems like that, but it's, with a dynamic programming solution, it's actually, the dynamic programming solution only really works because this is bounded, the sum is bounded. If it's not bounded, then this is actually basically unbounded, so the dynamic programming solution would probably run out of memory, actually, if it was a pretty large n. Yeah, potentially run out of memory. Well, it really wouldn't do anything. That's really the issue. It would just be extra memory for nothing. You would just end up, basically none of these nodes would collide with each other. And yeah, that's it. You would just have an exponential tree every level. It just doubles in size. And you'd be using a lot of memory too. So it'd be a slow algorithm that uses a lot of memory. So actually the DP is only possible because it's bounded. At least with this approach. If there's a better approach. So that's the thing. I don't think there is a better approach. I don't know. Let's see what the discussion says. I don't actually know. I don't know. I'm going to give up. DP is easy. Oh no. Don't give me that. O of n is iterative DP using subset sum with explanation. I feel like I'm being taunted. C++ 3 milliseconds. Whoa. 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 Iterative DP. I want to say this is just iterative. I mean, that's what I did, right? Iterative DFS. Yeah, that's kind of what I did. I don't know why. I think my solution was expensive because I used a. You know what we can do, actually? I bet you my solution would be a lot faster, too. It's technically a DP solution, but we can do. We don't need the pruning either, really. But you can do it this way. You can do, as I had suggested before, a vector events, a vector events. You can do it this way. Yeah, we'll call it memwise, and we're going to say n or nums dot size, and we're going to say yeah, we'll say the value is we'll start off at sums dot back. And these will all be 0. You can actually make it -1, do it that way. And then we're going to say try memoization, have a current total. We're going to actually make this initially sums.back. And we're going to do minus twice the value. And this will change. Actually, I want to go the other way. Okay. We don't need to make the key anymore. And we just say if memo of I, or current, and current total is greater than equal to 0, then return that. Okay. And if we're greater than equal to the size and our current total is equal to target, then we're going to set our memo of current and current total. It's really target equal to 1. Otherwise, we set this equal to 0. Oops. Okay. Remaining now, for the time being, we'll keep the pruning. We'll come back to that shortly. So memo of current, and again, current total. And finally, left plus right. Sure, something like this. See if that still works. Bye, William. Good luck solving these problems. All right, take care, Melik. It's good chatting with you. Talk to you soon. Appreciate you coming by and saying hello. That was kind of you. Or not kind, but I appreciate it. I'll just say that. Runtime error. Oh, did I keep my, I did keep my test cases. Nice. Nice. Heap overflow. I see. That's interesting. Wasn't expecting that. Why did that happen? Oh, is this why? No, the value I'm pretty sure is the second thing. Where and why does this runtime error occur? It's the thing I'm wondering. Huh. Oh. Oh. Wasn't expecting runtime error. Also, this doesn't make sense anymore. We minus twice the remaining. If that's still greater than the target, then we're not going to make it. Pruning changes a little bit. Yeah. Because all we're doing at this point is subtracting, so that changes a bit too. I don't think that's the problem, but where is this runtime error happening? I could not tell you why it's even happening. I want to say it's probably here, but I don't think so. I don't know. That's fine. So it's somewhere in the code, but why? How many times do we call check? Twice. Call check twice. One time. We call check one time, and then we have a problem. Oh, that's why. Of course. I was right. I was right about this. I was right. Oh no. Still a problem, huh? Okay. Oh no. Oh no. Oh. Whew. It's a good thing the code didn't disappear. That would have sucked. Oh no. Okay. I meant to redo. Undo my redo. Redo. What do you do for redo, right? It's... Anyway, okay. Undo and redo. So... Okay, what does this look like? A few times now, but then we get a problem. Oh, you know what? We do have an issue where... No, we shouldn't. It shouldn't be able to subtract... Oh no! Oh, I'm wrong. Oh. Oh no. For some reason, I thought we didn't need, oh, I see. Okay, I see the problem. That's my mistake. Got it. Yeah, okay. Well, it's a good thing we kind of sorted that out. There's an offset here. There's a small offset that you need to consider because it could be negative. I didn't really think about that. What? One, two, I think it's, yeah. I think it's me. I'm just doing something wrong here. I think it's me. 5, 5, 5, 5, 5, 5. Runtime error. 1, 2, 3, 4, 5, 6. Oh, that's why. Duh. Of course, that would have happened anyway. One, two, three, four, 5. What? I see. Is that why? Is that the issue? Is that the problem? Still a runtime error. Overflowed. What do you mean overflowed? No, no. What? What? Oh boy. Oh boy. What is going on? This is it's great. It's great. Oh boy. Alright. So we got a lot farther this time, but something's overflowing. Okay. So we got 5, -1. Now, how did that happen? Current total is -1. Okay, that's fine. Oh. I missed it. I missed it. There we go. Wow. Okay. Yeah, I have an offset total. Oops. Whoa. That's what I was describing before. I had the idea correct, but I didn't implement it correctly. Everywhere you see that, just update that. Okay. Okay, that's a little bit more efficient. 7 milliseconds for everything here. All right, let's give it a shot. Okay, that's significantly more efficient, right? That's kind of what I was saying before. So you can somewhat optimize this. Now the thing is, I don't think you necessarily need to. I don't think the pruning is entirely necessary. If we remove the pruning, how much faster does this get, or does it get faster at all? Oh yeah, it's quite a bit faster. And you don't need to prune anything. And because you don't need to prune anything, you don't need to do this either. Just doing fewer operations. So you can do just an accumulation here. You actually can make this even faster, I think, because these numbers are... Actually, never mind. No, that's not true. Okay, let's do accumulate. All right, how about that? What does that look like? Yeah, that's even faster. Nice. Okay. That's an improvement. That's an improvement. But we still kind of run into an issue where, right, like it's memoized, it's dynamic programming, but technically we can go even quicker. So someone had 3 milliseconds. I had 31 milliseconds here with this. What if we do this? Is that still correct? Might not be correct. Whoa, okay, no. No, you want that memoization. It's definitely better. It's a lot better. How do we get 3 milliseconds on this though? Maybe now we can try to write a DP solution from this one that we have currently. So we're definitely going to do this first. I'm going to comment out this whole thing though. Okay. So this is the DP part. There is a loop of some sort where we have, let's say int I equals 0, I is less than nums.size plus I, and we have this left side is basically f becomes dp of current 1 and current total. And then right becomes a similar thing. Two times this value, and this value is nums of I. It's something like this, and then dp of I and this offset total, which is the current total, plus this, so we'll call it offset total, yeah. Well, yeah. And that's equal to left plus right. And how frequently does this occur? When does this occur? How does this occur? What is this? What do we do here? So that's the thing I'm like not really sure about here. Do you just do this for all I and j over n? I don't think so. Maybe you want to say the number of ways you can get to a particular value, I guess. Yeah, maybe that's what we do. Okay, I think I got it. All right. We do something like this. Okay, just comment these out. So we'll start off at 0, and we're going to say for each, for I and j, now j is going to be less than twice that total plus 1. And we're going to say the number of ways that we can reach a particular value so I guess initially, right, we'll do it initially. We'll do an initial thing, or do an initial calculation. So dp of 0, also keep my voice down, how are we doing, 2 hours now? Okay. The first array will be the number of ways I don't actually know what we want to do. I don't know how we want to calculate this. If we say, let's say our function is the number of ways that we can reach a particular sum. And it's offset, right? Ironically, that's, oh, wait a second. Ironically, that's what we're trying to calculate. for a particular sum. That's not really what we want. Well, maybe that's what we want our DP to represent. Maybe, I don't know. If I had some function that gives you the number of ways for a particular target, how can we use that to generate the target we're looking for? Well, we could just do all of the targets as we add or subtract values. So we could take, you know, with the 0th element, I want to say something like you can initial vector where you can't get any of the target, everything's 0, the targets are 0, and then when you add or subtract from the top, if you subtract from the top the first value, you can get target minus the first value, and then from there you can add or subtract the next value from both from the target, or the beginning total, and from the one that has something. So if there's a 1 there, if there's something greater than 0, maybe you do it that way. Maybe initialize the beginning at 1. Okay, I think I have an idea how to do this. Okay, we said yes, num size plus 1. Okay, so the initial array is going to be dp of 0 and 2 times total is equal to 1, and everything else is 0, right? Now we're going to say loop from int j equals 2 times total to j is greater than or equal to 0 minus j. It really should be j greater than or equal to we say int val equals nums of I greater than or equal to val. And we're going to say dp of I plus 1, we'll say, of yeah, it's going to be dp of I, and we're going to say if dp of I of j minus val, or yeah, dp of I j is greater than or equal to 0. Now we're going to increment dp of I to be j minus val, add dp of ij. Okay, a little bit confusing, but I think that's the solution. And then at the end, we return. This looks totally different, by the way, from the other solution. From the yeah, this looks just completely different from the this solution, this recursive solution. At the end of that, we're going to return dp of nums.size, where we added all of the I value, we added all those I values as integers, and it's going to be the target, and that's what we're going to return. Yeah. What does that look like? Compile error. Nice. What? No longer memo anymore. Runtime error. Overflow. Some kind. Oh yeah, this is... It's no longer the value, it's actually 2 times the value. Which is kind of interesting, I guess. Does this make sense? I think something's wrong here. Hmm. What? Very confused. Where is the issue? Maybe it's here? Oh, it is. Oh, interesting. Well, yeah. Oh, I think it got optimized out. I think that was the thing. When I used return 0. Oh no. Yeah, it just optimized everything. But if the target's less than the total, then it should be less than. It should be. This should be fine. Am I crazy? For some reason this causes, oh, because that's why. That's offset. It's supposed to be offset. Forgot about that. Still wrong, but interesting. I don't think you actually need this edge case, by the way. Not sure that you need it. All zeros. Nice. Okay. Alright. So we start from the top and we subtract. I don't know if this is right either, by the way. I think oh no, it is supposed to be. It's supposed to be translated, I think. So it doesn't quite make sense. So J is actually going to be, so it's a little confusing. So it's actually, okay. So we're actually going to map, we're going to translate all the values upwards by adding total to everything. Yeah, so it's going to be i's from 0 to num size. J is going to be total, start off at the top, plus total, so 2 times total. And then J, you're going to subtract from J the value. So what we're going to do is all the values in the array really should be greater than or equal to 0. Oh wow, yeah, minus val should be, it's fine. Should be fine. Oops. So I don't know what I just did to my and we're gonna say dp of ij greater than or equal to 0. That index point, if that's true, then we're gonna subtract this value. Now what's interesting is it's 2 times this value, subtract 2 times this value, because we're going to flip from a positive value to a negative value, so you subtract it twice. Now that's a question, is that what we want to do? Yeah, I think so, yeah, because we're going to start off at, you actually don't have to do it this way, we can actually do, you can either add or subtract the value. So let's do it this way. Let's start off with the total is 1, and then we're going to go all the way down from the top. We're going to go all the way down and just say as long as and we're going to say j greater than equal minus value is greater than equal to 0. Well, it doesn't have to be that. It could be, yeah, we could do it this way. Minus j, we say if j plus val is less than or equal to 2 times total. And then we say if j minus val is greater than or equal to 0, really. And then we can do dp of ij is greater than or equal to greater than 0. We can do dp of I plus 1 of j plus val equals d plus equals dp of ij. Hopefully this makes sense. And then same thing, minus val dp of ij. Something along these lines. I don't actually know what we end up with here. So yes, we start off with a total of 0. There's one way to get there by adding everything together. Really should be, well, no, it's everything's offset by the total, so it's one way to get 0, which is actually not true. No, so we do have to do it the other way around. We add everything together, and we have one way to get there. And then we say we want to subtract or add our value. So we do have to actually subtract twice or not add anything. So we can, oh, wait. I didn't notice I even did that before. It should be plus, not minus. I mean, not equals. That was a mistake. Just in case some, oh, I did get it right. Okay. I was like, what? That's crazy. I don't know. Yeah, I was gonna say, I don't think we have enough test cases for this. To get this right. Because all of these are zeros. So what happened here? One, 0, 1, 2. Okay. Oh, my head hurts now. I have a headache. Ready for bed. Ready for bed. I'm gonna say I have a headache, but I'm just, yeah, I'm ready for bed, man. I don't want to stay up so late. I kind of knew I needed to add more test cases here. So why do we get a runtime error here? Why does that happen? Target plus total. Oh, yeah, we do have an edge case. Is that the only one? There's got to be other things that we fail on. Or I guess the other way around. Actually, it's kind of should have caught that one too. gotta be cases when this fails, though. Oh no, it's correct. Go figure. Yeah, I mean, this is, it's basically the same idea that I had before, where we, by the way, you can optimize this again too for memory, and only need to use one array. You don't actually need to use the DP of the whole thing. You can just do sort of previous and next kind of arrays, just 2 arrays, so you can optimize for memory. But it's an interesting solution. You don't need, you can do, also you can do 2 times the total, and then subtract twice for this value, and then not do any subtraction here. Just do that right here. That doesn't really matter, does it? Could do something like this, I think. Is it correct? Oh. It's a lot more milliseconds. That is many more milliseconds. Huh. It's faster. So this previous vector, and then we have this let's call it next vector. And we'll say if previous j next j. And really it's equal, not plus equal. We'll do plus equal. Yeah, that's okay. Because if we're subtracting down instead of adding up, go down further. Yeah, we want to do plus equals, I think. Yeah, never mind, we'll do plus equals. So the next is previous j. And then we just, at the end, we just set previous equal to next. And then this is just previous at the end of it all. I probably should have commented these parts out. Yeah. Wait, why? Oh. Alright, that should be fine. How do we do? How did we do? 64 milliseconds. No kidding. Total. How about this one? I have to think about how this works. If the total, which is a positive value, is less than the target, then we return 0, certainly. There's no way to reach that. If the target, though, is less than the negation of the total, excuse me. Which is the other way around. It's going to happen. Then also we return 0. Which is to say total target, right? So we can negate this. And say, or the negation of the target is greater than the total. Which is to say the total is less than the negation of the target. Very interesting. Total is less than the target, or the total is less than the negation of the target. Those are two edge cases where we have a problem. Have an issue. Now, this is a super interesting question, I have to say. Now, we don't have to allocate this each time, by the way. probably do have to set it to 0 each time, I think. Maybe I do have to allocate it each time. I take it back. Now, is there a way to do this that's even faster? I think so. We can go up, I guess. We add values. Can we do faster than this? I mean, this is pretty good. Faster, even faster. By the way, we don't need to do any of this anymore. We can just do don't need variable I in there anymore. You know what you can do? So you could say, let's do it the other way around. Let's do J is 0 to this total. Plus the value. Can reverse everything here. So 0 is everything is negative. And we say J is 0. J is less than or equal to 2 times the total. And we'll say if previous J is greater than 0, now we're going to add next J plus previous J, and we're going to say if this is greater than equal to less than or equal to 2 times the total, now we're going to take that value to that previous value of J, and so previous equal to next, and this is no longer going to be target plus total. By the way, so all the negations have been 0, and now we're adding things upward as we go up. When we're equal to the target, excuse me, you gotta actually subtract the total, believe it or not. Oh, no, I think we still have the two together. I think we still have the two together, I don't know. Okay, is that still correct? Huh. 40 milliseconds, alright. That is 10 times slower than the previous guy's solution. But this is quadratic with a linear space. Oh, yeah, quadratic of a linear with respect to the total values. Now should we use a hash map instead of a vector? That's a question to ask. I don't know. Do we need the accumulate function? Well, the only reason we need that accumulate function is that we want to use a vector instead of a hash map. Could just use a hash map and see if that's any faster. Let's give that a shot. I don't actually need a vector anymore. Don't need the total anymore. Oh no, previous is 0 equals 1. That's what we want. Still want that. Excuse me. I think it's clear erase or something, you know. I don't know. Well, let's do it this way for now. Okay. I and J. So previous to j is second, and j is just p first. And now we can say add the total, add 2 times v. Okay. And that works as well. No, is this correct? Compile error. Oh. I really need to go to sleep. How many hours are we doing this for? 2 and almost 3 hours now. I think this is just target now. Oh yeah, I don't think we need to do, we could just do plus val and minus val. Yeah. Oh. Oh, that's interesting. Well, the sum is 1. Excuse me. Oh, how do we initialize this without the total? We actually don't know. If they're all added together, all subtracted together. If we suppose that everything is subtracted together, then this kind of works out. But we need the total at the end. Yeah. Could do just the target, but then we need something to initialize this with. Can't be p of 0 equals 1. Have to start with something we know that we can get. And just create something of a tree from there. This is a different solution, by the way, than this approach, because of that starting condition. Excuse me. Let's see if this is correct. Let's start with that. Yeah, I don't know. Alright, I don't know. Well, we can kind of do this on the way here. Alright, how do we do now? Okay. Still correct, but very slow. Alright, so let's go back to what we had. Okay. Pretty slow though, overall. Not really fast enough. What we can do, we can put this in here. Yeah, speed things up a bit. Does that make it slower? Oh, faster. There we go. Yeah, because if we're going to do this comparison at all, then you can skip all of this if it's not if it's not greater than 0. Excuse me, and I guess you don't really need that comparator anymore, do you? I don't think that matters though. Yeah, not really. Hmm. 8 milliseconds. I think that was not a useful optimization, maybe? I don't know. thinking faster. I think I've solved this problem before. You gotta be kidding me. Oh. Oh yeah. I've solved this question before. It's a good one. It's a long time ago. Oh. Yeah, I've solved this before. I've seen it before. I don't remember how I solved it. Gotta go review that. I have a video on it. Actually, ready for this? I'll pull out my video. That's kind of funny. Let's see. Yeah, let's see my own video on this one. Partition equals subset. Give me one moment. Yeah, 4 months ago I looked at this problem. That's pretty funny. Wow. No kidding, I found it. Alright, let's see. Can you hear my voice? Let's see, hold on. It's kind of low though. How do we do? It's 16 minutes, not too bad. Alright. Let's see if we can come up with some, I don't know, let's just get some random input. Oh, it's gotta be less than 100, right? And it's possible of I. Doesn't seem good. That's what we had before. If this works, it'll be. Particular element is not present. So if you look at the intersection, there might only be one path that doesn't contain that element. So that's the one path. Now in that case, all the elements in that one path. Watching myself going over a problem is great. I'm just like, is it this way? Is it that way? Can you do it this way? It's great. That makes sense. What I ended up doing, I said, it's like the same code that I have here, sorted it first. For some reason I thought sorting it would be good. Again, plus target. True. Using pointers. Yeah, it makes sense, actually. I get it now. Really care. Sex. Yeah. It's like hours of this, huh? I should probably just skip to the end. Wait. values. So I got about 44 milliseconds. I've seen this problem. I've solved this problem before. It's really funny. All right. Tried the problem. It's an easy DP one. Well, actually, yeah. This is easy. Here we go. Beautiful. Got that 96%. There it is. That's what I'm looking for. Beautiful. Let's go for it and see what happens. What did I end up doing? Target. That's why. I remember now. Let's go for it and see what happens. Oh, hey, go. Four. That's and some over that. That's good. Time this any faster though? We're at like the difference between 240. Weird. Here's as we loop one. Oh, I don't want to say because this is related to the total number of possible values with regard to the sums. Actually this values for the sum squared because so by the sum basically probably your and they're bounded is going to have k summation. That means terminates pretty quicker. The sorting would cause you to terminate earlier because it's where you've gone past it. Huh. I couldn't seem to get more efficient than this. How to go fast and sort. I don't know. Well, was you can like keep adding small numbers to there's quite a bit of overlap. So might even be like cubic. No. Yeah. Let me do 2 pointers. I got 12 mils. Whatever. Pretty reasonable. We did alright. I really struggled with this problem. I'm gonna give this one an upvote too. I really struggled with this. Found this to be extremely challenging. I don't think it should have been that challenging, but for whatever reason, I really struggled here. I wrecked. Yeah. All right. You know. Okay. Pretty reasonable. We did alright. I got kind of wrecked by this problem though. I mean, we spent almost 4 hours on this. Within that loop we do, so what's the solution? Possible target. Huh. Excuse me. Yeah, I did a really similar thing to this. what I have right now for the DP solution. For each number, we loop over I equals previous, I is greater than 0, decrement I. Possible, and I plus x less than or equal to target. Possible is true. Previous less than I plus x. Previous equals I plus x. That's the closest we got each time. So loop down from that value. Oh, that's right. Yeah, you can optimize this. I forgot. That's actually the way that I optimized it. What did he say here? We did a DP solution for the subset sum. Find the target sum ways. I guess I never looked at the how, you know, like, to the extra information how to do that. Detailed explanation. Subset P of sum such that sum of P plus target plus sum of nums over 2 must be even. So sum of P minus sum of N is going to be equal to target, which means that sum of P is the target plus the sum of N. What did we do here? We added sum of P and sum of N to both sides. You get 2 sum of P is equal to sum, right, target plus sum of P plus sum of N, which is just the sum. Oh, that's interesting. Target. Okay. Let's add that in our code. Just edge cases. Target plus the sum. Oh no, oops. I was gonna say I missed some test cases there. Oh no. Alright. Okay. If the total is less than the target, or the the total is less than the negation of the target. Or the total plus the target is not or the total plus the target is not divisible by 2. Now he's saying that so I actually you can do things in kind of an interesting way here. You can say, you can actually use a pushback here. And we'll say, yeah, we'll start off at 0. And we'll say, next, J. It's really going to be, okay. Let's say, alright. J is less than or equal to, or less than, say, previous dot size. Do it this way. X equals previous J. Then next J, we're going to say next is at least the previous dot size. Now, yeah, we do less than 2 times the total. And then we'll say if P is greater than or equal to next dot size, push back. How about this? Does this still work? No. Nice. Oh. It does. Imagine that. Or it's maybe. Oh yeah, okay. But this is quite a bit slower than we just had, which is kind of odd. Wouldn't expect this to be slower. Whoop. That's a lot faster. Okay, so some cases it's a bit faster, some cases it's a bit slower. Overall, I think we did okay though. Very interesting though. Okay. Yeah, this is the same solution I had last time, more or less. The subset sum problem. There is a more efficient way to do this though. Which I'm sort of not familiar with. I kind of want to look at it again. Let's say tomorrow, sometime tomorrow I'll look at it again. I need to sleep. But I think this post is a good one. Accumulate sum. If it's odd, turn 0. Otherwise, subset sum nums of this divided by 2. Oh, yeah, okay, interesting. That's the target nums. And nums s, dbs plus 1 equals 0. db equals 1. In nums, is equals n. dp plus equals dpi minus n. dps. You gotta be kidding me, it's so simple. It's so simple. Really? You can actually do it within the same vector. Huh. N, I is S, I is greater than or equal to N, decrement I, dp of I is equal to whatever the dp of I minus N was. Number of times you get I minus N. And it's just N times N by S. Is that right? Is that right? That seems so simple. Well, because this is a little bit different than what I'm trying to do here. It's a subset sum. No kidding, really? I feel kind of dumb now. Isn't that simple? It is that simple. This is efficient, but not as efficient as that. So, get rid of all these things. Just call it a subset sum. So, we know that we have p minus n equals t. We're going to add a sum to both sides. Excuse me. P and n. N's cancel on the left side. Twice p is equal to target plus the sum. So p is so we're gonna get the sum total. Let's call it the sum. Subset sum. We'll say it's So if, what do we say, S has got to be less than or equal, so our target is less than or equal to the sum. Or sum is less than or equal to target, or less than target. And then we're going to return 0. What did he have over here? Hold on, he had something kind of interesting here. What, oh, I see, okay. I was wondering how I did this, yeah. Got it. So either of these, and is that what he said, sum less than target? It must be. Yeah. Okay. Sum is less than the target, or sum plus target modulo 2 is greater than 0, return 0. Otherwise, we're going to call our subset sum subroutine. And we're going to use so 2 values. We have vals, or just nums, yeah, vals, and then int target. And so we're going to use nums target. Now this target is interesting because it's going to be our target, or x, we'll say. It's going to be target plus the total divided by 2, or the sum divided by 2, which I never would have thought of this on my own, truly. I mean, it's not hard to see it or to realize it, but it would take me a while. And then this subset sum seems to be really straightforward. So we're actually going to have, we already have this sum, so we can do dp of vector size sum plus 1 and the way it works is we add, so now this is just the regular partition sum problem, and basically that's how many ways we can get a particular number. Yeah, I mean basically dp of 0 starts off at 1, I think. You can get 0 one way, and you would say 4 auto or 4. Or you just do it this way, I think, for int x. Not x, but, oh, yeah, okay. Call this t. X of vals. And we're actually going to loop over go from the top, so I equals sum plus or sum I is greater than equal to really 0, decrement I. And it's, we said I minus, now he used n, which is the value x, I think. You do dp of I is equal to the dp of I minus x. Increment this by that value. And then at the end of it, you're going to return how many times you can get the sum, or how many times you get t. I think it's something like this. Wrong. Okay, nice. So we're saying we have these values, we have this target t. We're going to say, okay, there's at least one way to get 0, right? We just have 0 elements. And we say, okay, for each value, we're going to take I from the top, decrement down, and we're going to increment I, that position of I, by whatever the previous calculated number of ways, whatever the previous calculated value would be if you subtract this value x. So the first number, let's say we had 111, right? So we would get the first time, so the total sum is 5. The first one we add, we would get dv of 1 equals 1 and dv of 0 is 1. And then the next one that we add, we would say dp of 2 is 1, and dp of 1 is now 2. So now we're using 2 different values, even though they're the same kind of number. They're different indices, I guess, these numbers. And then same thing, we get 3, we would get, so we have 1, 1, 2, or rather, yeah, 1 we'd end up getting there 5 different ways, but we can get to, 1, right, so the first value would go 0 is 1 and 1 is 1. Second value would say 2 is 1 and 1 is 2, and I think that's it, right? Then we would get to 3 is 1. 2, we would now add, there's 2 different ways to get to 1, and so the ways we get to 3 increase from 1 to 3, which is interesting. Not sure if that's correct. Yeah, we're now at 1 to 3. And yeah, I mean there are multiple ways that we can get there. So there are those 2 different ways, but also 2 different ways to get to 1, but there's already one way that we knew of. See, that's the thing I'm kind of not sure about this. I don't know if this is true, this solution. I don't know. I don't think I understood it. Oh, that's the equal to n. They're really equal to n. Oh, I see. Interesting. Well, yeah, I have that. Yeah, that's what I did. DP of 0 is 1. Yeah, I had the right idea. I think I did this correctly. Oh yeah, we used instead of using a vector, they used an array, which is probably what I should have done too. Yeah, actually I like that better. Let's use an array. Let's do that. Why are we using vectors for this? Seems silly. Seems silly and wrong. And I use integers so infrequently that I don't even remember what the right syntax is. Int. Oh, it's dynamic. That's why. Okay. No, it's... What? No, yeah, I like I said, I use it so infrequently, I don't even know. Is this true? What he's doing here? Yeah, this... Oh. Interesting. It's not the sum, by the way, it's the target. I don't know why I thought that. Variable sized object may not be initialized. How did... How did you do this? Yeah, this is kind of hard to understand, this part. Whoa, cursing. I can't tell if this is Java. Can't tell if it's Java or 01 knapsack. I'm looking for someone to mention that you can't actually do this part here. This is Java, but this is not right. You can make a vector like this, but you can't make a variable sized array. This needs to be a const expression. I'm pretty sure that's the case. And that's the compiler error I'm getting here. Excuse me. Variable sized object may not be initialized. Yeah. That's what I'm saying, man. You could do this. That's fine. Wrong answer, though. No, why might that be the case? Oh. That's why. That's my mistake. I don't know, I'm dividing by 2, but I'm trying to bit shift it twice instead of once to divide by 2. I was gonna say, I think my code is exactly what he wrote. Ooh. Yikes. Interesting. Yeah. It didn't handle this case. I've thought about this. I was like, I don't know if this case gets handled either. Well, target plus sum, it'll be negative, and so this won't get you a negative number. Yeah, that's interesting. I think, yeah. I think it's right. How do we do? Okay, pretty good. Can we do faster than 4 milliseconds? 9 milliseconds. 6 milliseconds. This is a lot faster though, definitely. It's definitely faster. I really gotta sleep. Alright, we got 3 milliseconds. We're close. Very close. We can rewrite this, I think, to be a little bit better too. This is very interesting, this part. I didn't really think, I didn't think this would be the truth. Yeah, you can do the subset sum. Okay. We can hard code this. How about this? This is really interesting. Oops, whoa. A really interesting portion here. Yeah, this is a really interesting part. I like this a lot. So this is apparently the simple solution to the partition sum problem. If you know the target. Yeah. Super interesting. This is really hard to understand or wrap your brain around. I kind of want to think about that a little bit more. So we're very close, but not perfect. Not 100% and not in the best memory either. Although I guess the way to do this with the best memory would be to not even do, to like brute force it without any memory. Something like that. Oh man, we're so close. If we could only get 0 milliseconds. If only we can get 0 milliseconds. I don't think we can get 0 milliseconds, by the way. I don't think it's possible. I don't think this optimization helps us very much, by the way, this part. I think if we can leave this out. Oh. I stand corrected. I stand corrected. Oh, I see. Okay, it goes kind of haywire if you leave that open. Ooh, I didn't realize that. That's interesting. Ouch. Ouch. Didn't realize that's how that worked. Oh, there we go. 3 milliseconds. Nice. That's probably as good as I can get. I don't know. I'd have to use something even better. So, I'll do one more. Super interesting. Okay. So why does this work is the question. Well, the reason is the first number, you obviously get 1 where that first number is and 1 is 0. And then it's very similar to what I had, but not quite the same thing. And the next number will add the number of ways you can get to the previous value. Yeah, I mean, I think it's exactly that. I mean, I think it's exactly correct. This is kind of what I had. Only difference is that I used 2 arrays. As it turns out, you don't need to do that. Because the values that you don't change, they stay the same. It's almost the same thing that I had, but a little bit different, a little bit smarter, I think. That's kind of what I was getting at before. I was like, there was like something I couldn't quite grasp. But yes, it has to do with the vectors going back through them. If you don't add a value, then pretty much the whole thing is the same. The parts that you do add a value. Since you're only adding 1 number at a time, you know you're only going to modify 1 part at a time. You can't go the other direction though. You have to go from the back to the front. And the addition that you make has to sort of go in the same direction, I guess. In that, like, you don't want to modify values that you're going into, if that makes sense. That's what I did, I think, incorrectly. Is that the reason why I needed a new array is because I was modifying values that I was going into, but you can go in one direction and then modify the values behind you, which is what's going on here. Is that we're going from the top of the back of the array to the front, and I guess the top of the array, back of the array to the front, and we're modifying each of those values with what is already sort of behind it, or already closer to the front. So we're not referencing values that we've changed at all, right? That's what makes this really clever. It's really simple, super clever, and really good. I like this a lot. Yeah, alright, fair enough. I'll have to basically memorize this for subset sums. I mean, it's kind of just it for all the subset sum problems, target subset sum problems, and then their variations, which this is a variation on that. Super interesting question. But yeah, so let me go. Thank you all for watching. I'll talk to you soon. Have a good rest of your night. Oh boy, that was fun. That was good. Glad I know the better solution now. All right, take care.